Hello, welcome to Toddcast number 21. I think actually I messed up the last one and called it 21 as well. So this is the second Toddcast number 21. Anyway, we're going to cover isomers today. We started into isomers last time. We talked about conformational isomers, different chair conformations, whether things were positioned in the axial or equatorial position. We also discussed gauche versus anti, staggered eclipse. Those are all conformational isomers, or the same compound but different position in space because the molecule contorted, twisted, rotated, whatever it did. So for this lecture, I want to sort of expand on that and just use the generic term isomers. So we've already looked at constitutional isomers, also known as structural isomers. I'm going to introduce a new category called the stereoisomer. So the constitutional isomer, or is also called the structural isomer, has different connectivity, so therefore different IUPAC name. So it may, in some instance, be called, let's say, 2-methyl propane, or actually that's a bad one, 2-methyl pentane compared to, let's say, 3-methyl pentane. Different position of groups, different connectivity, different bonds, so it ends up with different IUPAC name. So, for example, if you name both of these, this would be 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. This would be 2-methyl 3-pentanol. This would be 3-methyl 2-pentanol. So those are structural isomers because these two substituents have changed position. You actually have nuclei move from one bonded carbon to another bonded carbon. So those are structural isomers or constitutional isomers. There are also stereoisomers, sometimes referred to as configurational isomers. We'll talk about what those are specifically in a second. But stereoisomers, exact same connectivity. So these have different connectivity. Stereoisomers actually have identical connectivity, but they have a different spatial arrangement. So it could be because of rotation, or it could be just different right and left-handedness, for lack of a better word, certain chirality. So a perfect example is this molecule, 2-butanol. 1, 2, 3, 4 carbons with an OH on 2. 1, 2, 3, 4 carbons with an OH on 2. But if you try to superimpose, move this one directly over and make everything line up, the CH3s line up, the CH2, CH3 ethyl groups line up, but the H's and the OH's do not line up. If I try to rotate it to put the OH in the right spot, then the ethyl and the H won't line up. Or if I rotate it to try to make the H line up, then ethyl and hydroxyl won't line up. So somehow, some way, you cannot get all four lining up. So these are known as stereoisomers. They are, in essence, a mirror image or right and left hand of one another. Okay, so stereoisomers, for simple perspective early on, I'm going to refer to it as a carbon with 4 different substituents that has a different arrangement in space. I'm going to quickly learn, well, maybe not that quickly, but I will learn in time that there are other examples besides a carbon with 4 different substituents. But if you have a carbon with 4 different substituents, it will have the possibility of forming multiple stereoisomers. Either this one with the OH in the plane and H back, or this one with the H in plane and the OH back. So we'll get into more details about that as we go. Within stereoisomers, there's so-called optical isomers. So in this case, you'll note the Cl and the H have changed position, but the CH3 and the rest of the molecule is in the same position as far as this carbon is concerned. And then the other carbon, same story, the H and the OH have changed positions, but the rest of the compound has stayed in the same spot. So we will refer to these two as optical isomers because they will rotate plane polarized light differently. So what that means is light has an electromagnetic propagation, which means it has an electric plane where the electric wave is propagating, and perfectly perpendicular to that is the magnetic wave. Now, natural light is randomized. The electric plane might be vertical, might be horizontal, or it might be somewhere in between. It's a whole randomized scatter plot of different angles. When you put it through a polarizer, so perhaps you've had polarizing lenses before in your glasses, it filters it so only the vertical electric plane can get through. So it ends up filtering out, let's say, all the horizontal while letting the vertical through. It filters out half the light, but it makes it all align in a very specific way. And so if you really want a good example of this, let's say there's some seaweed growing in the ocean, It's all growing perfectly vertical. So that's kind of like a polarizer. It's a filter. And if you saw, let's say, a stingray traveling towards it, swimming towards it, and a halibut. Halibuts swim vertically, stingrays swim horizontally. The stingray could pass through it, but excuse me, the halibut could pass through it, but the stingray couldn't because it's aligned incorrectly. So half the animals swimming through the kelp bed would get filtered out. Bizarre example, but it actually works. So only if the plane of the animal, the halibut, is vertical and the seaweed's growing vertical, can it fit through. Same thing with light. Only if the electric plane is vertical will it fit through. If it's horizontal, it won't filter through. So that plane polarized light passes through one polarizer, so it's, let's say, only vertical. Then when it strikes that compound, either one of these compounds, it's going to interact with this compound because it's asymmetric. The light will actually interact and cause it to rotate. The plane that it's rotating through will rotate. And then when it passes through another polarizer, if you have it at the right angle, you can let all the light pass through, but only if you have it at the right angle, meaning they rotate plane polarized light to a known quantity. It's not random polarization, it's a certain amount. It depends on the compound and the quantity of it. I'll go into far more detail down the road on that, but just know that it can rotate plane polarized light, hence optics, light related, referred to as optical-isomers because they have different interactions with light. Geometrical isomers have different geometries. So we learned a little bit about it when we looked at double bonds and there were cis and trans, and we looked at cyclohexane, and you can have cis and trans substituents. So basically it's cis versus trans, E versus E. So in this case, the first one, the two substituents are trans to one another, whereas in the second one, they're cis to one another. So those are said to be geometrical isomers, non-superimposable, but they have the exact same connectivity. It's still an alkene carbon, two sp2 carbons connected to a methyl, an H, and an ethyl, a methyl and H and an ethyl. So same connectivity, but different alignment in space. Okay, so those are our fundamentals. So optical isomers we're going to talk about for optical rotation and interaction with light, geometrical for just, I guess, restrictive structures like rings and pi bonds for how the substituents are located. Okay, so let's get the definitions down. That'll certainly help, I think, in understanding this a little bit, or a little bit better. So geometrical isomers, they vary in their positioning about a rigid structural component, such as a ring, or like we just saw, a pi bond. This first group is cis, this second group is trans. So up as opposed to up down, cis and trans. Again, we're revisiting something you've done before. And then the alkene, the highest priority substituent on this one, ethyl beats H. This one, the ethyl alcohol group beats the CH3. So these two are on the same side. So same side cis, as opposed to this other one where they're on opposite sides, ET, E trans. Okay, so cis C, trans E. Optical isomers, isomers that are non-superimposable mirror images. And I want to emphasize they do not necessarily have to be mirror images. We're going to start with that for the ease and simplicity of it. But optical isomers can also have different differences at one portion of the molecule, be a mirror image in one spot, but not all of it. So for now, let's just start with isomers that are non-superimposable. That sounds good. Mirror images, I'm going to say for the time being, yes. Both isomers rotate plane polarized light, but in opposite directions. That's only if they are mirror images. So if they're non-superimposable mirror images, one will rotate it, let's say, clockwise a certain amount. The other one will rotate it the exact same amount, but counterclockwise. So that's these two examples. There is a mirror in the middle. If you can see it right here, the CH3 reflects, the C reflects, the OH reflects, the H is in back in both, it reflects. So you hopefully can see a mirror image for that. So we'll get into that a little bit more detailed. Specifically, enantiomers are what I was describing. So enantiomers are non-superimposable mirror images, i.e. reflections of one another. They exhibit the exact same physical properties. So your right glove and left glove, even though they fit on each hand, should have the same everything. Same thing here. the enantiomers, the R version and S version, or the left-handed and right-handed version, or the D and L, depending on what science you're in, they will exhibit the exact same physical properties, meaning they will have the same density, they pack together the same solubility, they're going to interact with different compounds the same, index of refraction, meaning they're going to bend light the same amount, they're going to boil at the same boiling point, same melting point, any physical property, they're going to be the same. So I want to consider this structure right here, which is 1, 2, 3, 4, 5 carbons with a chlorine on it. So it is 2-chloropentane. And I'm going to put a mirror plane here. So here's my mirror at an angle. So this is going to come in, and I'm going to draw the reflection. So those are the things going in. I want to point something out for those of you who have not taken optics in terms of physics. But when you see a solid line, that represents a real ray. So it's a real ray of light coming in. The dashed line represents a virtual line, or an image that leads to a so-called virtual image, or reflected image in this case. So this is traveling through, and this dashed line represents virtual, meaning if I'm here, I look here, my reflection will appear to be behind the mirror over here. If I'm here, my light goes through, it's here, and it will appear to be on this side. So when you see your reflection in the mirror, you see yourself in the reflected and inverted mirror reflection state, the same distance from the mirror that you are from this front end of the real mirror, or you're the real image is the same distance from the mirror as the reflection. Key thing here, though, the ethyl, excuse me, the propyl, my mistake, reflects the propyl, carbon reflects the carbon, methyl reflects the methyl. I could do the Cl as well, I could do the H as well, but started to get a convoluted diagram. Hopefully that seems clear. Hopefully that's reasonable to you. So enantiomers are mirror images, and they exhibit the exact same physical properties. So which of all molecules are chiral? And then mark the chiral compound, or the chiral carbon, with an asterisk. So I want to start by pointing out that a chiral carbon is one that has 4 unique substituents attached. That's going to be our first lead-in definition. It's not the definition of it, but it's a really good starting point. So this carbon right here, let's consider what it has. It has on it a Br, a Cl. This represents a methyl group, and then there's an undefined H on there, meaning this group, if I point out that, has 4 different substituents on it. So I'm going to say that's chiral. This carbon right here has a CH3, an H, a Br, and a CH2CH3 attached to it. So this is the same thing we had here, but one more carbon, which means this carbon right here is chiral because it has 4 things attached. This has no chiral carbon, but that doesn't mean, for now I'm going to say this is not chiral, but I'm not going to blindly say alkenes can't have some chirality to them. Again, we'll recognize that down the road. For this compound, if I rotate it by 180, it's the same compound. So no chirality, no mirror. So when it reflects, its mirror image will be the same thing. And then finally, I have a carbon here. Let me do it in purple. That I think has 4 things. 1, 2, and then, oh shoot, those are equal. So let me just keep moving out. So let's see, still equal. Oh, darn it, still equal. So this half of the ring and this half of the ring are identical, meaning this is not chiral. So you do not get a chiral center there. I thought I was going to get one because I definitely have 2 different substituents here and here, but that's the same. If, however, there was a CH3 here, then that would be a chiral center. But I don't have that, so not a chiral center. Hopefully these seem okay. So we're basically, at least in the beginning, going to be looking for carbons with 4 different substituents. That's going to be our guiding light at the beginning. We'll make it more elaborate probably in about 2 to 3 lectures. So want to know how to draw enantiomers. So one of the easiest things to do, if I want to draw a reflection, I want to put a mirror here. And if I do that, I'm going to get H3, C, CH2, CH2, line, methyl group up, H and back, OCH3 here. Okay, bear with me, because what I want to do is I want to take an axis right about here, let's say. I want to rotate it by 180 degrees. And I'm going to redraw it over on this side. So if I do that, this CH3 will come all the way over here. Looks something like this. We'll go down to that carbon, which now the H, which used to be in back, when I rotate it by 180, will be in front. The OCH3 will be in back. And this group will be CH2, CH2, CH3. So the mirror image rotated around. Rotated around won't change from being a mirror image. But the take-home message from this, sorry, this thing is looking so glitchy today. Sorry about this. So hopefully that is a little more clear. Note that this group is in the same spot and this group is in the same spot, but these two change their position. So the easiest way to draw it, you can draw the mirror image and rotate it around if you want, or you can try this new and improved lazy way. So I'm going to get rid of everything that's here. So take whatever notes. I guess you can just rewind if you needed to. I'm going to clear everything and say, change the position of any two substituents. The two we learned were these two. So if I draw this thing the same and just switch those two. So anytime you do that, you're going to get a mirror image. So again, here's this. If I rotated it by 180 around this axis, I will get the mirror image. Everything will be like, this will be in the plane on this side, this will be in the plane on this side, like this. OCH3 in back will be in front. H in front will be in back. So 180 will show the reflection. So kind of cool trick. Anytime we change any two substituents, I chose these two, but could have been these two, it could have been those two, could have been those two. Any two substituents, if you change them, the chirality of that center changes from one designation to another. If there's only one chiral center, that's how you go from an enantiomer to the other enantiomer. So you're going to keep on hearing me say things like the R and S. So it's a designation for which enantiomer we get, and I'll go into that in the next lecture, but it's just ways of designating a chiral center. Okay, so want you to look at these and start making a decision which one are configurational isomers and more so enantiomers. So if I consider choice A, CH3 is in the same spot, CH2, CH3 is in the same spot, but notice the H and I have changed. So how many changed? 2, therefore they are enantiomers. So which one represents the same molecule and not a pair? So that one's out. This one compared to this one. H stayed the same and ethyl stayed the same. But CH3 and OH changed. 2 changes. Means these two are enantiomers. Okay, so apparently there is no right answer so far. Let's see how this works. I have, let's see, in this next one, the Cl changed positions, the Br changed positions, and the CH3 changed position. When 3 change, so basically the Cl went up to there, Br went down to there, that went there. 3 changes, it's the same molecule, rotated. All I did was rotate around a bond, meaning they're the same. So which one represents the same? So far, C. Not sure if this is multiple choice, but we'll figure it out in a second. The very last one, let's see what changed. H is in the same spot, Cl is in the same spot, but the ethyl and methyl chloride groups change. So 2 changes, therefore enantiomers. So guess what? This must have been multiple choice. Not a surprise, and important that we go through each one. So 2 changes, they're enantiomers, 2 changes enantiomers, 2 changes enantiomers. When 3 things change, they have the same molecule rotated to be in a different 3-dimensional space. Not bad. Hey, some more practice. So in each structure below, identify a chiral carbon, then draw the enantiomer. Okay, so that's going to take a little work. So for this first compound, let's see, sp2, so nope, 2 H's, 2 H's, 2 H's, 2 H's. Ah, here we go. There's my chiral center. So I'll get rid of the circle because it said make an asterisk. Asterisk. Just to make sure these are all sp2 all the way around. That's not a carbon. That's not a carbon, CH3. So this is the one and only chiral center. So again, the easiest way to do it is to change any 2 centers. So I'm going to make the ring stay the same. So what I'll do then is I will now make this and I'm rotating it in a way so the CL, the CL is actually in the same spot. I've just rotated back and rotated up. So as long as it's one away from the connectivity, and then if I draw this and H like that, that is my enantiomer. Same compound on one side, and then 2 groups switch. Easiest thing to do is switch the back to in front and the front to in back. If I would put the CL there, it would have been fine just as well. Okay. So ibuprofen, a common NSAID, non-steroidal anti-inflammatory drug. Chiral centers would include, let's see, right here, I think. So help me out and double check. There's an H. There's the rest of the structure. There's a CH3 and a CH3. So nope, CH3s are identical, so not a chiral center. This one here, CH2, that's not, can't be possible. sp2 all the way around the ring, can't be possible. sp2 carbon there, so this is my only hope. So I'll put a star there. I'm going to emphasize that this is a CH3 group. And I'm going to put the H right here. So 4 substituents, the benzene ring with the t-butyl group attached, para, the carboxylic acid group, the methyl, and the H. 4 unique substituents. So the easiest thing to do is to switch the 2 smallest, the H and the CH3. So I'm going to draw my benzene ring. I'm going to add this group. And then bring this one over here. And this time, I'm going to put the CH3 in front and the H in back. So the enantiomer, 1 chiral center changes. This is actually that straightforward and that I don't want to say easy because I'm doing just 1 chiral center, but it is that systematic. So if I had 4 chiral centers, I'd change all 4 to make the enantiomer. So all the chiral centers have to change to be enantiomers, and that would mean I have to switch 2 groups at every single one of these centers. Okay, not bad. I think I'm catching on to this. So let me get rid of my ugly drawing and let the picture comes in and show it. So notice, same thing here. Those 2 groups switched. This group switched. Everything else stayed the same because it wasn't chiral. Okay. Oh my gosh, even more. So let's see how we do this. So L-threonine, and just want to point out, amino acids, typically they're L. For natural amino acids, there's going to be a few really rare instances like bacteria cell walls, which will contain a D amino acid. And it's actually because we only recognize L, so our enzymes are specific for building and breaking down L amino acid connectivity between amino acids in a protein. So the bacterial cell wall, by making it D, and it's specifically an amino acid called alanine, they put a D-alanine into their cell wall. We don't have the enzyme to break it down, so therefore we can't destroy their cell wall. So they're able to just have this impenetrable sheath around them to go inside of us, and we can't do anything to destroy it. So clever design. But in this case, let's see, CH3, nope, this carbon has an OH, an H, rest of the amino acid part, and shoot, definitely a chiral center in that case. And then this carbon right here has an H, an NH2 alcohol group, and a carboxylic acid group. So this actually has two chiral centers. So to be an enantiomer, you have to have two changes. So I'm going to draw the skeleton the same as before. But now both chiral centers have to change. So the OH has to be in back, and the amine group also has to be in back. Beta D glucose. And if you were taking bio, and they mentioned beta D glucopyranose, that's also the correct name for it. Pyran or pyranose would be a six-membered ring. So beta D glucopyranose would imply a cyclic form of glucose, although beta, it can only be beta and alpha just represent cyclic forms. And that's getting way ahead of ourselves. That's a 311 topic, but just want to emphasize what these mean. The key thing, this is cyclic glucose. So how many chiral centers? Well, here's one, and it has an O, the carbon part of the ring, this carbon dangling off the OH, so CH2OH, and an H in back. This is a chiral center because it has the group going up to O, the rest of the sugar, OH and H in front. This is a chiral center. This is a chiral center. And this is a chiral center. So we have 1, 2, 3, 4, and 5 chiral centers. So that's pretty substantial. So if I wanted to draw the enantiomer, I would have to change at every chiral center. The purple one would have to become OH in back. The green one would have to become OH in front. The blue one would have to become OH in back. The yellow one, OH in front. And red one, CH2OH in back. So this differs in 1, 2, 3, 4, all 5 chiral centers, making the enantiomer. So for what it's worth, this would be, if you're hanging on to this information, this would be beta L-glucose. And then this would be D-threonine. Okay, so hopefully this seems reasonable and viable to you. So I'm going to let the structures kick in. So I'm going to erase what I've drawn. So it's all gone in 3, 2, 1. So again, both chiral centers change. And 1, 2, 3, 4, 5, all 5 chiral centers change. So hopefully this seems okay. Hopefully this is not so bad for you. So you change a chiral center by changing any 2 carbons. I'm going to refer to these as chiral carbon. I will use the term chiral center, which is kind of a misnomer, but we use it commonly in OChem anyway. I'm going to sometimes call them a stereocenter, which is also kind of correct. And then stereogenic carbon, which I think is probably the most correct of all the terms. I'm going to use my terms loosely because everybody usually does. I'm not going to worry about the formal definitions of any of them. But for now, just note that it's a carbon with 4 unique substituents. That's what we're going to focus on early in this chapter. Okay, so that Thursday, week 5 means that I have hit the end of what I'm talking about here. So I will pick up the next podcast where we'll go into a little more detail on exactly how we distinguish one enantiomer, one chiral center from another. Have an absolutely wonderful day, and I will hopefully see you in class soon. Bye.